Yes, so first talk we have Jingyuan Meng and Guillaume Peruchet. They're both from Bartlett. Jingyuan is digital fabrication design tutor and robotic technician at BMate, and Guillaume is researcher in computational design and robotic manufacturing, and today they will talk to us about applied robotics in the built environment.
Cool. So, can everyone hear me? Yes. So recently, in recent years, in the field of architecture, in the field of architecture, there's a growing interest of researching robotics-related research. So today, basically, we will present how Bartlett School of Architecture integrate robotic technologies within the built environment. So BMADE stands for Bartlett Manufacturing and Design Exchange. Our faculty is situated across 2 sites within UCL. So the robotic faculty itself is considered a group of individuals with interdisciplinary backgrounds.
So our robotics inventory encompasses a variety of robotic arms across different ranges and across different reaches and payloads. And we have a breadth of tools to facilitate a plug-and-play approach across 3 main areas, which are additive, subtractive, and transformative manufacturing. Our main focuses are the teaching and research, and these are within computational design and computer-aided manufacturing in architecture. So our main focus is how to combine material analysis together with computational design and computational models to create integrative robotic processes to create performative-driven architectural structures. So these are some of the projects that we have developed with the students at the Bartlett. These are 2 projects of subtractive timber milling, which both are similar in that each of the components that compose this multifaceted design is unique. And so the robotic process was developed at the same time as the geometry, and that allowed for optimization in material and in geometry for the overall structural performance. Then we also investigate non-standard manufacturing methods, such as on the left you can see a clay carving method which was applied to the development of acoustic components, and on the right a wire cutter that we used for a process of stone wire cutting, which was then applied to for timber frame footings, which is inspired by a Japanese earthquake prevention traditional method. And then onto transformative manufacturing. 2 of the processes that you see here is on the left, incremental sheet forming. So incremental sheet forming is a process in which local plastic deformations are introduced gradually into thin sheets to create 3D geometries. And this project in particular was investigating how these how these gradual deformations can be introduced to enhance the performance of these thin sheets. And then on the right, this project was a project of rod bending. So it was a collaboration between a performance artist and a robot, in which the dancer was creating its performance, and this was captured in motion data and then interpreted by the robot and captured into this process of bending the wire, so that there was this dialogue between dancer and manufacturing process.
So the robotic 3D printing project within BMA, we are trying to subject we have two main methods. So for the standardized material, we tend to push the fabrication method towards the boundary and then trying to investigate the novel printing methodologies. For example, the student Lawrence Hu, who's doing the space frame printing out of the PLA material. And the other method we're working on is hybrid materiality. Instead of, so in order to fit certain functions, like the best example will be the BioID student, Natalia Purica. She's using wood-based PLA and then to cultivate the myceliums for insulation as the insulation material. And then the mycelium will consume on the wood particles within the PLA filament so that it creates a quite robust bond in between the two substances without adding additional adhesives. And we also work with quite a lot of biomaterials, including melanin, hydrogel, food waste composite, and also agro-industrial waste composite. But however, in the recent years, there is a significant challenge of scaling up of the bioprinting projects to architecture scale. And that's why this project, Calcareous Arabesque, is actually successfully demonstrate that the biomaterial can be printed at the architecture scale. And the project is led by Professor Marcus Cruz and Dr. Brenda Parker. Basically contributing to the net zero emission by 2050, Tit and Lao Sugar approached to the BioID lab and seeking for the upcycling solutions for their industrial waste residues. And the two main waste they're dealing with is bagasse and participated calcium carbonate. So the BioID lab actually regenerate the material based on their material properties. For instance, bagasse is a lignocellulosic residue. It has a low thermal conductivity and also a really good soundproofing properties. And then so that we compress the bagasse onto the back structure of the cassette to form a homogeneous mid layer with high level of surface texture. And this will basically enhance the bonding strength in between the bagasse and then the extrusion material on top. The participated calcium carbonate is a byproduct from the sugar refining process. It's being currently used as soil treatment, as a soil fertilizer to treatment acidic soil. And then after a series of rheology modification, we finalized the mixture that is capable for extrusion, and at the same time, we managed to control the shrinkage within 10%. And the use of the industrial byproduct is being optimized for up to 85%. So in order to encounter all the limitations and then the risk of low materialities, we kind of gradually we follow the method of integrated scale-up method, where we are trying to consider the material design and then fabrication as a whole. And also this workflow will allow us to transfer the most essential data in between each stage, from the smaller scale to the full scale. And then the design. So the three-dimensional pattern is produced by a self-generative algorithm, differential growth. And we are doing the calibration of the print at the same time with the computational design, because we wanted to transfer the key calibration data, for instance, the extrusion width as well as the layer height, and deliver to the design group so that they can so that these data could be the constraints for, for them to set up the algorithm. So the final panel is resulted as a 4-meter high and then 2-meter wide architectural wall component. It was displayed at the Waste Age exhibition in London Design Museum. So this project is not only showing the potential of incorporating bioprinting within the architecture field, it also highlights the responsible use of the waste material.
So this is another research project we conducted in the last year, and it's about the automation of COP construction. So in here we were interested about how we can combine energy efficient, reusable, and locally abundant earth-based materials with building technologies, with advanced building technologies to create materially efficient structures. So this process is called, or we call the variable aggregate impact printing, and it consists in the aggregation of soft particles of heterogeneous material with so it's formed of clay, fibers, which is straw, and stone aggregates, which are assembled by the robot. Then there's a scanning feedback to more accurately calculate the position and orientation of the previous deposited layer, and then so on is gradually the structure gradually is constructed. So we investigated the material behavior, and we standardized the material composition, and we conducted structural performance tests to optimize the material formula. We developed some tooling to overcome the challenges that are introduced into a process which utilizes heterogeneous materials, and specifically large stone aggregates, where we are able to pick, orient, place, and compact soft particles. And then, so as I mentioned before, these particles are placed because they undergo complex and unpredictable deformations. We need to introduce a step of scanning in order to accurately place the second layer. And then this process of robotic, the freedom that we get from a 6-axis robotic arm plus the scanning allows us to a lot of freedom and customization to build structures, and we've successfully built arches and load-bearing structures. So that's.
Okay, thank you. I wanted to. Sorry, I have one more sentence. I wanted to thank for our BMADE faculty sitting on the back. Without you guys, we can't accomplish so many projects, and also we have a lot of students here today. So they have some of the project you have seen on the screen is actually displayed in the lobby. So feel free to swing around our table, and then we have people will explain the projects. Thank you.
From the audience? If not, I kick off with one. Very interesting interdisciplinary research. You mentioned at one point that you are doing communication between the performer and the robot for manufacturing certain thin structures. I'm just wondering what was the goal of that project and how this communication partnership actually impacted the outcome of that project.
Mike? So the goal of the project was to create the performance. So this was a project from a master's program at here East called Design for Performance and Interaction, and the interest very much there is about creating, well, just that, performances and new modes of performing. So yeah, the aim was to create a well, a metaphorical communication, no, between the dancer and the process, so that it becomes like a reflection or a dialogue between these bend structures that become like then the materialization of these gestures of the dancer and so on. So it's like a poetic computation project, let's say.
Thank you very much. Thanks a lot. Thanks for your time.
For an introduction, I'm Alex. I'm the associate professor in robotics and AI. I'm very glad to share my personal journey, research journey, how I build robots and develop new technologies in terms of robots that can move with agility and really manipulating like human level of dexterity. So that's my personal story. Happy to share my journey. Right. So I start my PhD work by doing locomotion on humanoid robots. Then along the way, I have developed all the technologies for robot locomotion, for humanoid robot, quadruped robot, and etc. And after solving the locomotion problems, the mobility is no longer an issue, and I turn my attention to other capabilities such as manipulation, how to manipulate small objects in daily life, and also deploy this technology in the hospital, in the warehouse, and etc. So in our group, we are really looking at solving all these 4-stack solution for general robot motor skills. So let's start with locomotion, the mobility issue. This work has been done in 2018, quite some time ago. So unlike the Tesla auto driving, which is more like navigation problem, avoid collision and etc. So this particular look at the physical interactions. So how you can learn from human demonstrations, from real data, which is very, very difficult to simulate. So it's almost impossible to simulate all these things. And in terms of minimum viable prototype, we build all this setup in the lab in order to test it. So humans just need to teleoperate and show several examples. And from this real data, and we can use a particular neural network structure to capture the memory in order to learn how to operate these things. So no matter what happens, this little boy will just get up, recover balance, overcome obstacles, steer it around, and deliver the parcel at your door. So that we show that the capability of a tracked and a wheeled robot. And more difficult problem is that how we can achieve animal level of agility through legs, like what we see with dogs. And for that work, this paper has been published in Science Robotics as a cover for the December issue in 2020. So let's look at the performance. So in the real world applications, it's really, really hard to say that I guarantee my robot works all the time. So the robot should have enough intelligence to handle all these unexpected scenarios. It can be kicked over, knocked over, pushed over in all possible ways. And the robotic systems have to be resilient and robust to all these things. So what you see here is that all these are newly learned skills. Look at the moment how it gets up and start to walk and turn around. All this has been synthesized online in real time. So the neural network controller, the experts are pre-trained in the simulation, but when you use it, the central gating network, there's a central network that is grabbing different experts according to the situation and synthesize a new network online in real time. So that new network can have multiple expert skills in order to handle all possible situations. So you can see the outdoor test that the robot is very, very resilient. It will just try all the possible way to get up and resume balance. So here is the crash test, which we can't do in real robot, as you can see, right? You let it fall, and then it can, even in a blind setting, it is able to negotiate with obstacles. And the most incredible moment is the following. Just pay attention to the tiny, small movements. The precise timing and action, how to retrieve legs without getting stuck and turn with 3-point support in order to reduce the friction and really spin the body so quickly and then coordinate and put leg down again when the heading is right. So you can see all these tiny, precise movements are generated online by the neural network without any pre-programming. So we save the labor. So instead of having a 30-man team spending several couple of years to manually program things, what we need now is, in this case, one supervisor, one PhD student, plus a cluster. So it's the new, it's like the steam engine era. Like we really dedicate a lot of this computational intelligence to computers. So once we solve the locomotion problem, we can transport the payload from one place to another. So what's next? The robot needs to do something in dangerous scenarios to save human life, for example. And so human operator can stay in a safer zone without risking our lives. So first thing I look at is grasping. So again, if you look at all the daily objects, soft objects, textiles, clothes, they are very, very hard to simulate. So can we learn directly from real data? The answer is yes. So here, as you can see, the previous slide is the learning from demonstration setup. So if we demonstrate reasonably representative situation like a small, big, and large, and soft, medium, soft, or hard, so we combine them, we can get about dozens of different representative demonstrations. From this demonstration, we're able to generalize what is the feedback control law that humans use to grasp different sizes of objects with different stiffness, shapes, and etc. So you can see that almost all the daily objects are able to be grasped using this learning from demonstration framework that uses real data. Okay, no simulation, that's real data. Okay, so just to give a quick view, of course, it's very difficult to show hundreds of objects. Just a quick view that almost all the daily objects, which is not too heavy, like not more than a kilograms, things like that can be handled by this dexterous grasping framework. So next, we look at how about objects that's smaller than our fingertip size, right? We can grasp something really, really small. So we think about what we can do with the new generation of tactile sensor. So the moment tactile sensor is still quite large, it takes time to miniaturize them. So let's say we build up a proof of concept system, which is a gigantic two-finger system using arms. Okay, so this is the pinch grasp. Let's call it pinch grasp. Yeah. Okay, let's try to play it again. All right. So this is the autonomous operation. The user only needs to demonstrate one example. So that's a new case which has never been seen before. So it's a bigger test tube. And you can see the tiny movements. They learn from the real data from one trial only. And can see how it rotates and grab the object that's smaller. So like how we use our soft tissue in our fingertips. So we actually rotate a bit to grab it. And the beautiful thing is that because it's learning the fundamental principles, it learns the feedback control. And if you push it off, you can see what happens. So it's all learned from one human example. So it's pretty much like for control guys who are familiar with spin damper, it's pretty much like you just need to demonstrate, give me an example of spin damper, feedback control law, and then learn that in one line of equation from the data instead of learning hundreds of thousands of different spin damper trajectories. So we're really learning the control feedback policy behind the human demonstration. And therefore, it allows us to extract the human skill from only one demonstration data and real data. And that becomes possible. Right? We don't need millions of samples from simulation. That's no longer the case. So as you can see in just now the video, it can also grasp different fruits, vegetables, which are in the same category but slightly different. And it is robots adapt with certain variations. So in this case, we can see that we solve a fine manipulation. So we solve the dexterous grasping problem and fine manipulation in terms of pinch grasp. So what's next? Next is that robot can manipulate things, grasp things the same as we do. And there are still cases where we need human. And then, therefore, we have a very good multimodal human perception, human-robot interfaces that allows human to take over when it's needed. And that allows us to demonstrate really, really complicated, long-time horizon manipulation tasks. Here, we can see that it's really, really difficult. And what you have seen here is very realistic in the R&D labs, in the bio labs, or in the logistics, in the warehouses. From the beginning till the end, everything is done by the bot autonomously. Right, so opening the drawer, open the cover, picking things out, and then open another cupboard, take things out, put things in back, push the item to the conveyor belt, press the button, the machine is complete, right? So everything is done through learned neural network, where we apply the similar structure, as I said before, for locomotion. The same principle applies. Okay, thanks for the inspiration from my colleague Lorenzo from Queen Mary, because he said that's definitely possible to be done in manipulation. Why don't you try it? And I tried it, it worked. Just to wrap it up, time is tight, and I'm always here, so ask me a question later on. There's very important information I need to push out. So inside the group, I've done the visual, a lot of things. Not everything is present today, so I've done the visual perception to really disambiguate, to differentiate different objects in a very ambiguous situation. We can identify the right object. We're able to use new tactile sensors to do very fine manipulation. We can also learn from one trial data, and we can have multi-skill learning that can really achieve long horizon complicated tasks. And if everything fails, we still have haptic tele option in place. So the new thing we are working now is how we can use natural language to do planning. So everything you have seen here is imagined. It hasn't happened. So the robot will look at what is the scenario now. You give it a sentence as an instruction. Can you pick this box and put it on the ground? And the robot will imagine what is the sequence of action you want to do. And it allows you to plan ahead of time and see what's going to happen. And there are more interesting work we are doing in this direction. So we are very, very close in terms of solving the real-world autonomous robot problem. And for this, we call for more collaborations, because we are not the expert in natural language processing, and so we need more collaborations. And everything together can be put in an ecosystem where you have the data, you learn from real data, and you can scale in terms of connecting thousands of robots in this planet, and then you augment all these capabilities. For stack solution, I'll skip that. Again, so the final last bit to glue things together is natural language-based planning. And we are very, very near, close to that. So the final bit is humanity-based call. Sorry, that jumps a lot. Is that, so recently, in the past few weeks, I'm calling for the ART initiative. So it's an initiative, non-profitable initiative with like-minded scientists from everywhere. We're all interconnected. So we volunteer our time together to make this happen. So we are very, very close to get the general purpose robots. So the reason is very simple. In 2011, when Fukushima disaster happened, people asked me, where are your robots, Alex? It's not there. So the earthquake happened recently. They're asking me, where are your robots? It's not there. So it's a time. We're so close in getting technologies done. So we are so close to create life-saving robots. And let's do it together through the ART initiative and join us. We can transcend humanity, and the future is now.
Thank you very much. Thank you so much for your presentation. Do we have any questions from the audience? Then I start with one.
Sure.
That might be not what you expect. So I have a 13-month-old kid at home. And this is sort of, you observe how he's learning to grasp, how he's trying to hold things, grab them, put them in the right place.
Yeah.
And I find that really fascinating, moving towards this whole machine learning, having this old machine learning conversation is going on, and also the fact that we are trying to copy how humans grasp things, or how humans are doing things in robots. I'm just wondering, and obviously I'm not in the robotics field.
Sure.
How much study has gone through or looked into learning from how kids start to explore the world and learn how to manipulate the stuff within your field?
Within my field, I will tell you with the best of my knowledge. From my area, from my work, I'm not looking at that. So I know some of my colleagues are looking at that. They're looking at videos, observations. But to the best of my knowledge, I don't think we have very concrete understanding, what is happening there, because there are a lot of semantics, a lot of background information going on there. And it's very difficult to look at baby, look at the video, and how to extract because we don't know what the process is going on inside the brain. And another aspect which I know a little bit more is that the brain is an analog computer. So every time when you interact with something, there are a lot of molecular chemical reaction going on in the brain. And that chemical reaction actually is equal to a lot of bits of information we do in computer science in terms of neural networks. So they are completely using different principles. And what I'm sure about is that we still do not know how this analog computer works through all this complicated molecular computation that's done in the brain. So I believe that is still open question.
It's a very fascinating field. Thank you so much. Thanks a lot for your time.
Did you say?
Next we have research fellow in soft material structures from the Department of Mechanical Engineering. And her talk is titled Bubble Worlds, a Social Interactive Structure. How did refugees experience COVID-19 lockdown?
So, hello everyone. I'm Dr. Azadeh Shariati from Soft Robotics and Haptics Lab. And today the project I want to explain for you is a bit different from my own work, and it's actually an artwork. It's a social interactive structure named Bubble Worlds, and it's about the psychological experience of refugee during COVID-19 lockdown, and it's a part of a Trellis program by UCL East, which was a collaboration between researcher from UCL, me, and Professor Helge Wuderman, an artist based in East London, Duncan Patterson, with co-creation with a group of students from Code Your Future, which is a institution for teaching code to refugees, and artists from Rosetta Art. So, approximately 3 years at the same time, we've all bombarded with bad news about COVID. We had a very uncertain future and we all were in fear. So imagine you just came to UK and you are isolated in your new community and isolated from your old community because of geography. So these people are even double isolated and might suffer a lot. So it wasn't research because we didn't know the outcome. It was more co-creation and collaboration. And we wanted to explore how did refugees experience the COVID-19 lockdown. And we have done this through co-creation with students from Code Your Future, artists Duncan and Larissa and Sylvia, and the student from Social and Haptics Lab. Sorry. I need voice. Is it the voice? It's maybe I just, because some of the slides have voice. So we have done this through several workshops. The first workshop was a creative workshop covering audio, visual, and poetry. And you can see here some artwork of our participant. Here you can see a cocoon shape, a structure, and another artwork. And I need to mention that we try to consider social, legal, and ethical aspect, and we have consent form for using the video and record and voices. So the main idea just came from the first workshop, and it was a cocoon-shaped structure, which is like a shelter and protect people from the bad news. The students showed that they made conscious decision to block out negative news and focus on the positive connection with nature, and they focus on non-material thing in life during the lockdown, and they focus on self-awareness and self-growth. So our final structure was something like this. You can see it has, it's like a cocoon shape. It's not symmetric, and we used natural elements like bamboo and natural color for the structure. The second workshop was about describing the artwork in poem style expression. And here you can see a poem by William Blake. It's written by one of our students: to see a world in a grain of sand and a heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour. So if you remember, the shape of the structure was, the color was somehow again resembles sand, and we asked the student to read this poem in their own language. They read it in Turkish, Farsi, and Ukrainian. و یک آسمان در یک گل وحشی بی نهایت را در کف دست خود قرار ده و ابدیت را در ساعتی از زمان. And you can see the artwork, the shelter again was made of the artworks of our students. The structure, we want to give life to the structure, so we add breathing elements using soft robotics to the structure. We invite the student to come to UCL. We had some workshop on robotic element, and here you can see within simple experiment, we were exploring to solve some challenges we had during inflating and deflating the system. And here again, you can see that some students are making their own soft robots and learning about electronics behind the robot. So the structure has, as I mentioned, it has a breathing element to, and the sound was quite nice when it was exhibited. It really resembled breathing. And the artist I have worked with was a computational artist, and he used codes to simulate patterns inspired from nature, like octopus skin reaction. And actually, it was our joint interest, because I'm a soft roboticist, I'm interested in octopus, and he was making octopus reaction. And it was the reason that we collaborate. And you can see here different patterns that made by coding. He also had several workshops to teach this coding to students, and then we reflect this pattern to inside the structure. It's inside the structure. And I should mention that the video is prepared by Trellis team. And we have an exhibition last May in Art Pavilion London, featured in The Guardian and London News, and also second place in Robot Design Competition International Conference of Social Robotics. And yeah, it's the complete video. The sound, it's the exhibition. It's really the William Blake poem by Farsi. And yeah, this structure has a great potential for educational things, like education in, for example, in architecture, teaching coding, robotics, and different aspects. And also, it was an example of interdisciplinary knowledge exchange between artists and researchers. And actually, it can be used to explore reactive environmental exposure in neurodevelopment disorders. Thank you so much, and thank you all my colleagues in SOF Robotics and Haptics Lab.
Thank you so much for a very nice presentation and a very interesting topic that you covered, very important as well. Is there any question from the audience here? Sir, yes.
So I generally feel like it's a very beneficial kind of structure to like all of us on the individual, or like as an individual quiet in place, because even though we left the COVID, we still just seems to be like emerging from one crisis to another. So like what kind of things can we make to individualize this kind of structure, like to make sure to like kind of personalize for people's kind of emotional state, etc. What's your opinion?
I think, for example, from the outer, there is a specific design that is suggested by artists, but I think it has great potential to be personalized, and you can change it. You can change it to whatever you like. For example, the inter environment or outer. Yeah, I think it has potential to be personalized and using for education as a creative module.
Thank you very much. Thanks a lot for you.
Next we have Elliot McGee, who is a research fellow with interest in neuroprosthetics design and control and surgical simulation. And his talk is called Development of Surgical Tooling with Haptic Feedback for the Speed of Surgical Simulation.
If you need the pointer, it's this one.
Hi, so I'm Elliot McGee. I'm going to be talking about development of surgical tooling with haptic feedback for the Speed Up Surgical Simulation platform. For those who didn't see the earlier talks on this platform, it's a platform with three main intended uses. One, surgical training, so that trainee surgeons get more time using the tools in a simulated environment before they do their first operation on a real human, so they are a bit higher skill. The second use is for when surgeons are operating for very difficult cases, they can put in specific patient anatomy and practice for the specific case before going into difficult surgeries. And the third use is to increase the speed and reduce the cost of development of new surgical tools by giving the chance to actually use them before you go far down the development path, so you can do proper testing with surgeons and figure out if what you're doing is worth doing. So I'm going to cover a few different topics. First, I'm going to do an overview of hardware. This is basically the positional haptic hardware that we use. Then fixtures. These are the connection point between our positional haptics and the surgical tools. The development path we use when we come up with new surgical tools to use in the system. Some of the surgical tools that we have come up with, the current development work, and the future work. So these are the three main systems that we use. The SimuTouch 1 is one set of twinned robots that give each control 3 degrees of freedom to give a 4 degree of freedom that we can control with a free axis of rotation. The SimuTouch 2 is two of these systems kind of side by side where we can change the separation and change the height of them so that you can do a bimanual procedure. And then we use the Happily Inverse 3. This shows one robot here, but we can connect up to 16 to a single computer, but four is what we'd use for a single user. And this is a low-cost version of the other systems, but is a single robot, whereas the other is 2 robots or 4 robots. So the fixtures here, you can see the SimuTouch style fixtures where we have 2 points of connection and then free rotation in the middle. In the center, you can see the kind of hot swapping that the Happily robot comes with. And on the right is the fixtures that we're currently developing for having 4 of the Hapley robots together. So this will give you a similar level of control to the SimuTouch 2 with the Hapleys, but for an order of magnitude less cost. So development of the surgical tooling. So first of all, we have a conversation with a surgeon. We discuss the procedure that they're interested in simulating. We do an analysis procedure, so how do the tools interact with the patient? How does the surgeon interact with the tools? And we go through that analysis. We then pick a vertical slice. The reason we pick a vertical slice is at the moment we can't switch between tools whilst the surgeon's doing a procedure. They can't themselves change the tools. So we take a vertical slice of the procedure where they don't need to change tools. Once we've done that, we check the specific tool requirements. What exactly is the interaction with the hand? What exactly is the interaction with the patient? And we look at the parts of that that would be physical hardware and exist in the surgeon's hand, and digital hardware and exist purely in the simulation. Once we've done that check, we might have to, we hopefully can just take a tool that we've already designed from our existing library, or we might have to design some new things. So this could be haptic hardware. It could be that the tool that they're interacting with actually needs a certain degree of haptic interaction with itself. So for example, if you imagine a laparoscope, you squeeze the handle, well, the handle itself needs to give haptic feedback, not just the positional feedback with the object you're interacting with. We might need to develop a new digital tool. So an arthroscope is a tool that we commonly use. So you do a small porthole surgery, and the end of that tool has a different fitting depending on the type of procedure you're doing. Are you reaming some bone, or are you kind of removing soft tissue? In either case, developing a new tip for that is purely a digital tool. There's nothing being developed in the physical world. And then we might need a new tool itself. Perhaps they want to use a tool that we haven't developed yet. Well, then we need to design the tool both physically and digitally for use. And once we've done that, that gets added into our library, and we can loop back through, and that's added to our things that we can more easily simulate. So here are some of the basic tools we use. These are the earliest tools we developed. Syringe and a drill. So that drill can freely rotate, but then is controlled with 4 degrees of freedom and allows you to drill the patient. The syringe, similar thing, but the actual injection has no haptic feedback. That's one of the features we'd like to add, but currently we don't have it. And then a more recent version of the drill, which is just to hook into the Hapley system, but quite a simple prototype that we put together. For the arthroscopic tools, the video's a bit fast, but that is the setup we have. So you have the reamer in one hand, and you have a camera control in the other hand, and these work to give you a control with the haptics. So the tip where they connect to the robot is where your haptic interface is. And rather than being 3 degrees of freedom, we technically have 4 degrees of freedom, because the port that we have acts as a passive robot. It's holding the position there. So with this, we have a bimanual simulation with 4 degrees of freedom in each hand. But again, we aren't controlling for rotation. This is one of the limitations with this setup. But for an arthroscopic tool, although you do rotate the tools, you don't actually get much rotational haptics anyway, so it's not particularly important that we don't have that. It's a thing we'd like to have, but isn't necessary for this setup. When it comes to laparoscopic tools, rotation becomes important. If you have a grasper and you're grasping a bit of bowel, for example, there's quite a difference between grasping like that and coming in at this angle, and you need to be able to rotate the tool to the correct position. But the tool itself has haptics, as you can see. When you're squeezing the handle, you actually get a varying degree of resistance based on the bowel that you're squeezing. You can also see some of the tool tips. These are the digital end effectors that exist in the simulation. Just a simple grasper, and then also a clip that can be placed onto an organ to cut off circulation that is used in some procedures laparoscopically. So the main thing that's missing from this one is the rotational feedback. So this is the current thing we're working on, is the development of rotational feedback. So we have 2 solutions. One is the solution for the kind of the passive robot setup, where we have that port acting as a passive robot. And so we have an additional robot used, which rotates the end of the tool so that we get that rotational feedback. The other solution we're working on is a more complex one, requires an active motor between the 2 robots that will correct the rotation as well as giving reading the rotation of the user. That's further down the development path, but will allow you to control rotation not just when you're using a port, but will also control the rotation with a freely moving tool. Now, endoscopic spinal surgery is another point we're working on. When it comes to bimanual procedures, for things like the arthroscope or the laparoscope, we're actually lying to the user within the virtual reality environment. Their hands are actually separated slightly from what they are really doing. And the reason for this is that the robot holding the end of the tools would collide if they were actually realistically separated. So we slightly increase it, and to a user in VR, they can't tell the difference. With an endoscopic spinal surgery, one of the tools is the port that the other tool goes down, so they have to be in line with each other. So we can't lie to the user. They physically have their hands together. So this is one that we are, again, working on. I'm in the middle of building the first bimanual system with the Hapley robots. And as soon as we've got that working, this is the next thing, is to get this working. This procedure is a complex procedure. Only a handful of surgeons in the country can do this procedure, and it's taught in a different country if you want to learn how to do this. So we want to teach people how to do this in this country. The future work we're looking at the moment is, one, enhanced haptic tools. So by this, I mean several of the tools I showed you were lacking haptics where we want them. So for example, the syringe, when you want to inject or pull from a vial, for example, there is no haptics feedback on that as we currently have it. We would like to develop haptic feedback for the syringe and also build a generic haptic module so that for newer tools that we're developing, we can easily add in the haptics. Live tool swapping is another thing we'd like to add. So as I said, we can't currently swap the tool in the middle of a procedure while the surgeon's in the environment. They can't put a tool down and pick up a new one. We would like to add this. Doing so would make the width of our vertical slices of procedures allowed to be much wider, so you can do a more complex sequence of events. We have a few solutions that we have thought up that work with tools that use a port and solutions that work with tools that don't use a port, but we don't currently have a solution in mind that lets you switch between a tool that's in a port and a tool that isn't in a port. And then, of course, as we do our work, we work with more surgeons, we work with more procedures, we continuously grow our tool library so that we can more easily work with any particular surgery. So, any questions?
Thank you so much. Thanks a lot for also sticking to the time. Do we have any questions from the audience? If not, I start with something that I sort of, I'm also interested in. Working in the field of robotics and surgery, dealing with humans, virtual reality, what is and how much is the role of empathy in your application?
That's a good question. I haven't really considered it because I would say the empathy is largely important towards the patient, but we're not dealing with the patients, we're dealing with the surgeons. And as such, I don't think it's a thing that we've really considered. We have to consider how the surgeons use our tools, and that's actually an important step, is that usually what we do is we have a quick, mild conversation with the surgeon without going in too much depth of the kind of thing they are interested in. We'll then whip up a demo of that and bring them back. And we're not surgeons, so we don't really know what things are supposed to feel like. We can take an educated guess based on the toughness of the tissues and things like that. And the surgeon comes in, they hold it, and they go, nah, that's not right. And we immediately have to work with the surgeons on getting things right. But our lab is actually physically based in the Royal National Orthopaedic Hospital. So we have very easy access to the surgeons, and we have a kind of constant conversation with them, and we keep bringing them back in to have a look at each version of the simulation until they're happy with it. So I don't know if that counts as empathy, but there's certainly an ongoing conversation with the surgeons.
Brilliant. Thank you so much. Thank you very much for your time.
Yeah. Hi. So next speaker is going to be Nina Digren, who's a research fellow at UCL Interaction Center. And she's primarily interested in embodiment, engagement, and design. And her talk is titled How Understanding the Role of Instrumental Affective Touch in Occupational Therapy Practice May Support the Development of Collaborative Robots in Healthcare.
Another one.
Yes. You can use the clicker or the mouse. They're both set up.
Okay, thank you. Hello, everyone. Good afternoon. And thank you for letting us talk to you today about our project. So today, I'd like to talk a little bit about a study we've been conducting recently around instrumental affective touch in occupational therapy practice, OT practice. And the aim of this study is to understand touch and its complexity and how this might support the development of robotics, social robots, and collaborative robots in specific settings in healthcare. And this particular study was conducted by a team of 5 researchers and academics, Raffaele Buono, myself, Liang He, who is also here, and Perla Maiolino and Nadia Bianchi-Bertuz, and it's a collaboration between UCL and Oxford University. This study is part of a larger project called From Sensing to Collaboration that started about a year ago and is investigating embodied intelligence. In particular, it's investigating the development of autonomous systems in these several different domains, from social care to manufacturing, logistics, agriculture, and inspection and survey. And in particular, the project is interested in understanding more comprehensively the notions of perception and action and the social action and interaction in different settings, so that these autonomous systems could actually learn alongside humans and develop throughout their lifespan. And here's all the PIs are on the slide here, but of course the team is very large. We have a number of researchers on the project, as well as partners and collaborators, and we're generously supported by EPSRC. So occupational therapists and instrumental affective touch. This study builds on the notion that there is a need to develop collaborative robots and social robots in healthcare. And in particular, this particular study was informed by a systematic literature review on instrumental and affective touch that we conducted last year. And this research demonstrated that, that the touch is never just instrumental, and that also has this affective quality. And what we mean by this is, for example, if an occupational therapist uses a motion or grip to move a patient's leg, that there is a possibility that that same touch that's used to conduct this instrumental task can also convey affective qualities such as reassurance, confidence, or security. And the motivation from robotics perspective is kind of fourfold. I mentioned working alongside OTs, for example, is one area where collaborative robots could support occupational therapy practice, such as in task in dual handling, which is one of the main methods in moving and handling patients, such as demonstrated in this illustration on the slide. Robots could also support the training of OTs and families, especially there is one gap in, huge gap in the training currently, is that there's a lack of bodies that simulate particular conditions such as scoliosis or, for example, babies. It's hard for occupational therapists during training to know exactly how much pressure to exert on a baby's skin or their body. And this takes a long time usually to learn in the professional world. So if we could somehow develop robotics that can also support that already in training, then that could be very beneficial for the occupational therapists who are coming out from training and entering the professional world. And yeah, in rehab as well, robots could accommodate for a variety of lack of resources and staff. And there's this notion of embarrassment, because touch is very intimate, and it can also evoke these more complex feelings, such as the notion of embarrassment, both on the side of the therapist as well as the patient. So what I'd like to focus on today is the last point here, so the complexity of touch and its holistic nature. I just want to draw a little bit of a picture of the work that we've been doing to demonstrate this complex notion of instrumental affective touch. Our research questions for this study tackled three sort of main areas. So touch in interaction. So what roles does touch actually play in OT patient communication? And then we were interested also in these touch modulations. So if there are any ways in which touch, for example, pressure or speed or other dimensions of touch are changed according to the patient's affective state. And of course, as we've been talking about social robots, we also had interest in how OTs may provide assistance to patients, and whether a patient simulating robot or, for example, a part of a body or an exoskeleton could be designed to support different parts of training. And our methods were twofold. So we conducted 10 individual semi-structured interviews with occupational therapists, asking them about how they use touch as part of their practice, and we tried to probe quite deeply into the qualities of touch and how they communicate through touch in their practice. And then we also conducted an exploratory workshop with 3 stations targeting the kind of practical touch. So we invited them to reenact different scenarios with simulating patients, and then a station that's tackled different types of affective scenarios, such as pain, embarrassment, jealousy, envy, love and tenderness, a variety of different types of affective scenarios that therapists might encounter in their work. And then lastly, skin sensations station, which was investigating the different types of physical manifestation of different type of skin, for example, sweat, color of the skin. We're interested in what sort of cues they read in the patient's body. The findings from this study, there were 6 qualitative themes. The first one being the socio-affective dynamics of touch. So it very broadly painted the picture of what it's like to be an occupational therapist and then use touch as part of that very complex socio-affective landscape, which basically means that oftentimes a therapist goes into a patient's home and there's a myriad of variables that change. For example, the family members might be present, there may be nurses present, there might be different types of elements in the house that need to be moved around so that different type of treatment can be actually conducted. So the whole myriad of different types of elements that come into play in occupational therapist practice. The second theme was roles in touch. So who should actually touch the patient? For example, if we have a child patient, should it be the occupational therapist, or should it be the child's own parent who actually does the treatment and the touch in that instance? So questions around that. We also found that touch modulations were an important part of occupational therapists' practice. So occupational therapists were very aware of in a holistic, embodied way of the patient's condition. And this basically meant that they were very attuned to the patient's affective state. And they were interested in not only in the instrumental tasks such as developing new seating, but they were also in the moment when they were interacting with the patient, they were aware of how they use touch. And touch as an iterative process, so in terms of changing that touch throughout the course of a patient's treatment course, for example, in the beginning, if a stroke patient's learning to walk again, the therapist may use more pressure as part of their touch and then decrease that pressure over the time when the patient gains more confidence. Patient's affective state and physical cues, I already mentioned something about that, so being very attuned to not just the verbal, but also the physical cues of how the patient's presenting themselves in a sort of whole body way. And then challenges to effective touch. So sometimes a patient does not want to be touched. There might be embarrassment present, or there might be pain, or there might be fear. And this then creates more complexity to the interaction and sometimes hinders it completely. So the treatment becomes more difficult to complete. So I'll just go through briefly some of these themes more closely. So the roles of touch. The occupational therapists were mentioning that sometimes there are specific therapeutic benefits if, for example, a parent touches their own child who is the patient. So the occupational therapist would be more likely to teach the parent to touch rather than touch themselves, because touch is so intimate and personal. And some of the patient spouses were asked to provide sort of like stroking hand touches on the patient's head, and occupational therapists were saying how they wouldn't necessarily do these types of loving touches themselves, but they would rather get a family member to do that for them. Again, because touch is intimate, and embarrassment was one of the themes, and we can talk more about this in the poster if you're interested. I have some examples of embarrassment there. And patient's affective state and physical cues. So I already talked a little bit about the very sort of person-centric, embodied, holistic understanding of the patient from a whole body perspective. And again, this is something that we could talk about in more detail if you come by the poster. Lastly, I will show you just a few examples of, or maybe just one example of the touch modulation, which might be interesting because it sort of demonstrates that there are very subtle, I don't know if I can get the video to show, for some reason I can't. There is a little video, but I don't know how to, oh, there it is. We conducted this reenactment station as part of our study, and we gained some insight into the actual touch modulations where, for example, the speed of touch, the tempo, and let's see, the pressure would shift. This is an example of touch modulation where therapist instrumental touch in response to client's affective state of pain actually fostered client's trust. So there was a very subtle shift in the way that the grip changed. The therapist lessened their grip when the simulating patient was expressing sudden pain. And so there was this response of increased trust from the patient's side towards the therapist. So concluding thoughts, touch is very complex and needs to be fully understood. And when we talk about touch in healthcare settings, I hope that I have given you a flavor of it not being just instrumental or affective. So it's not just a pat on the back, but actually the instrumental touch can have these affective qualities. So we really need to understand more in which ways we can harness this affective quality and understand it to improve efficacy and effective outcomes. And on that note, thank you very much.
Thank you very much for your very nice presentation.
Thank you.
Very important topic, very impactful.
Thank you.
You actually touched on the element of trust
Yeah.
at the end. As you mentioned, just dealing with the trust between the therapist and patient is already a challenge. Introducing a robot in the whole equation makes it even more challenging. So I'm just wondering if you have looked into that, and if so, how are you thinking of overcoming the challenge of trust with the robots for treating the patient?
With the robot, yeah. So I think in general, the sort of general sentiment that we got from occupational therapists, especially with regards to helping in tasks such as dual handling or simulating a robot simulating a patient, it was a very welcome thought, because there was this idea that actually the therapist could gain confidence because they had this opportunity to practice alongside a robot or with a robot, and the confidence of the therapist could then directly support the formation of trust. And of course, in occupational therapy, the relationship of trust is usually built over several months, and usually therapists visit the patient maybe once a month, if that, so it might be very long periods when they don't meet each other. So it might be interesting to learn more about how a robot in that situation could either, support, or how might that shape a robot's presence, how might that shape the formation of trust, whether there's a similar time scale in the actual patient practice. Of course, we're not there yet, but yeah, as I said, especially in terms of OT's own training, it seemed that they were welcoming this, and there's interest in gaining that confidence and trust as a result of that. Thank you. Thanks. Yeah, of course.
The last talk, it was supposed to be presented by Dimitris Kanoulas, who cannot be with us, but we have Valeria Modungu, who is a research fellow interested in robotics learning, in particular control and planning, and he's gonna present the work, and the work is titled Robots with Legs and Arms.
How does it work?
Cognition for real world
You can put it on the
local
lanyard,
manipulation
like
complex
Okay.
environments.
It's perfectly fine.
Like this? Okay. So, hi everyone, my name is Valerio Modugno, research fellow at UCL East, and today I'm gonna give this talk on behalf of Dimitris Kanoulas, which cannot be with us today, unfortunately. So the talk is about cognition for real-world local manipulation in complex environment. So first of all, a little bit of advertisement here. So as you know, we have opened recently a new building at UCL East, which is inside the Olympic Park. So it's a very neat new structure with plenty of teaching research facility. And actually it comes with this amazing novel robotics lab. So we just recently installed the hoist, by the way, and we really invite all of you, I do really invite all of you to come and visit, because it's an amazing place to foster research and collaboration. So, okay, and in terms of local manipulation, another very interesting thing is that Dimitrios has recently won this Future Leaders Fellowship, which is about, it's called RoboIke, the project, and is about allowing quadrupedal robots to traverse complex and uncertain environments. What we think to do in this context is to use an higher understanding of the environment in order to get more animal-like behavior to traverse very complicated scenario. So let's set the stage for local manipulation. So what is local manipulation? Local manipulation is the combination of two words, locomotion and manipulation. So the idea behind that is to design behavior, figure out a way to combine locomotion and manipulation in a natural way in order to achieve very complex behavior that are close to human-like when it comes to humanoids, or when we think about quadrupedal robot, we want to get the same things, but by using different kind of structure. So what is happening here? On the left, what you see is what has been done so far. The, let's say, classical strategy that try to tackle this kind of problem, like navigating in structured or unstructured environment, has been failing so far. As you can see, the robot down there, the spot that is trying to climb this pile of rocks. The reason is because the robot does not understand what is happening. It doesn't understand the scene. What we think is going to be a key in order to get a better understanding and, let's say, a successful behavior when it comes to this kind of environment is to understand what the robot is looking at and plan and control the robot accordingly to this highly cognitive understanding of the scene. So as you can see, like in a way that imitates human and animals. So why we want to do that? I mean, the objective of this research is to develop like technology and control strategy to bring a robot in context in which now, I mean, there are humans doing these kind of things, which are very dangerous, sometimes are harmful, and even there is a chance of death. So we really think that it's going to be a deeply game changer when we will be able to deploy our robotics platform in context in which we would like to not have human doing things. This is a very, let's say, fast breakdown of the laboratory in which I'm working now. So my laboratory is the Robot Perception and Learning Lab. As you can see, I mean, we are many people here, and we do a whole bunch of things. So in order to tackle the problem of local manipulation, we try to develop algorithms that start from the low-level control to the high cognitive things, because, I mean, developing things like in this vertical way allows to design strategies that are very effective in achieving complex tasks. So we work around perception, control, and design and planning, using, of course, machine learning, deep learning, etc. So we do have many platforms, actually, in order to carry out our research. As you can see today, probably have seen the two robots down there, the small one, A1 and Go1. We showed some demo downstairs. Actually, no, this floor, because that's ground floor, in which we're showing some control techniques, optimal control techniques, and the reinforcement learning strategy in order to get nice and stable and robust walking behavior. We do have other platforms as well. We do have a B1 robot, which is just recently arrived. And we have a Boston Dynamics, which is a pretty neat platform, which allows for high-level control, mostly planning, and an animal from ETH Zurich. We do have as well, let's say, older things that has been used in some of our research, which allows to easily test planning strategy without caring too much about the balance. So now, let's say, we were talking about logo manipulation, so let's break down things. We started with, in the laboratory, by studying the problem of manipulation, so the grasping problem. So as you can see here, we have two different contributions to different lines of research. On the left, we were studying how to develop novel gripper, which were intrinsically safe, mechanically safe to manipulate soft tissue, such as vegetable or fruits. And this is still an ongoing research. And now we're trying to develop a reinforcement learning strategy to command this novel gripper. And on the right, as you can see, we develop technology for learning how to grasp without human labeling, which is a very interesting approach, which speed up a lot the generation of grasping policy. Another take on the robot manipulation is what has been going on in collaboration with the University of Leeds under the Telemann project. So the aim of the project is to teleoperate this quadrupedal robot in order, so there is a human teleoperator which is equipped with IMU on his body, and the idea is to command the full body behavior to the quadrupedal robot in order to achieve a very complex task. And this is, as you can see, is a teleoperation application for the logo manipulation as well. So in terms of logo manipulation, this is a slightly older publication, 2021. Here, the objective of the research was to design an algorithm that was capable of, let's say, figuring out where was the trash in the scene, classifying, labeling each of these objects on the ground, and then being able to go there, pick the trash, and put in the right bin. So this is another very interesting application for robot manipulation problem. Again, very different, but still, let's say, connected with respect to the logo manipulation problem, is this application in which The objective is to do 3D printing using these mobile manipulators for, let's say, large structure, because I mean now the 3D printing now has been done using, like, let's say, encased structure, but the idea is to go outside this and surpass this kind of framework. So here the objective of the problem was to design optimal trajectory to lay down the material in order to build this 3D structure without colliding with the former structure, the one that has already been developed by the robot. And then more recently, we have been working about the problem of navigation among movable obstacles, which is, let's say, a different take on planning problem in which we don't want to do only collision avoidance, but we want to interact, we want to manipulate the obstacles in order to figure out a path toward the goals. So we recently published this work on your left, which use more classical planning approaches, while we are actually developing novel techniques that employs reinforcement learning in order to find a viable policy that navigates the robot while moving obstacle towards the goal. And finally, yeah, I mean, this is the work which I'm mostly involved with. So we are trying to design novel control strategy and reinforcement learning techniques, let's say, application of reinforcement learning, and figuring out even combination of these two words in order to design stable locomotion policy for quadrupedal robots. We aim to develop this kind of agnostic platform controller, and I mean, and this is all built, let's say, it's done towards more, let's say, cognitive approach to the navigation problem. I mean, that's all from me. Thank you very much for your attention. And if you have questions.
Thank you very much. Thanks a lot for sticking to the time. Thank you so much for covering for Dimitris. It's unfortunate that he couldn't make it.
I know.
I think it's quite important to get to know about your exciting work. So thank you very much for covering for him. I guess you know who to contact in case you have any questions, so I don't put you in a challenging position today. And thank you everyone for your time, being here, attending, and thank you so much for all the speakers for providing us a wide range of application of robotics, multidisciplinary research, and so on. I would like to invite you all to please move after this session towards Gustav Park, where we will have our final keynote speaker giving you a talk. Thank you.